Yeah, that's for sure. My voice is the weirdest thing.
Okay, so
Oh,
we're
I
going to be
missed.
talking about sequences today. This very basic introduction to sequences is hopefully something you've seen before. Maybe not presented quite the same way. We might be using some more advanced notation than you've seen. But it should be something you've seen before on how you actually find a sequence and what are some of the basic sequences that you can work with. So today's kind of a basic introduction, and then kind of one of the ultimate goals of this chapter is to represent any function as a polynomial function. So let's say I want to take e to the x. E to the x is harder to work with than a polynomial function. What are some advantages of polynomial functions? Easier to plug in. And take the derivative of. Or integral of. They're a lot easier to work with. So if I could say e to the x is really, and I should have this memorized, but I don't yet, is really like 1 plus x squared plus x cubed, then it would be a lot easier to work with. So that's our ultimate goal, but today's kind of our introduction day into just sequences in general. So when we say a sequence, it's just a list of related numbers. It's some sort of pattern that we have found. And notation-wise, you usually show a sequence as a sub n, where n is an integer. And normally, n starts at 0 or 1. Most common, it starts at 1, but it can also start at 0. Occasionally it'll start at like 2 or 3, but you're saying a sub 1 is the first term, a sub 2 is the second term. It's a list, a sub 2, and then the ellipses just mean keep going in the same pattern. So when we say a sub 1, we're going to have some function with n in it, like if it was 2n, if a sub n equal to 2n, then to find the first term, we'd plug in 1, because it's the first term. To find the second term, we'd plug in 2, because it's the second term. It's counting up by 1 every time. So first we're just going to look at this pattern. One of the big things they usually do when you're starting out sequences is toothpick patterns. How many toothpicks would I need to make each of these? So how many toothpicks would I need to make the first box? 4 toothpicks. 1 for each corner of my square. How many toothpicks would I need to make the second?
7.
7. How many toothpicks would I need to make the third? 10. What about the last one? 13. So right now we know our sequence is 4, 7, 10, 13. We could keep going in the same pattern. What would come next? 16, 19. What are we doing every time? Adding 3 every time. So between each of these terms, we're adding 3 each time. So what I want you guys to spend some time thinking about is I want you guys to come up with a formula. If I know I'm adding 3 each time, I could find the next term. We call this recursive. If I know the last term, the previous term, I can find the next one. So if I want to know the 7th term, how are we going to get to the 7th term? We have 4 terms right now. How am I going to take it up to the 7th? Add 3. A couple more times. This is first term, second term, fourth term. What would my 7th term be? 22. 5th term would be 16. 6th term would be 19. 7th term would be 22. What if I asked you to find the 100th term? Do you really want to keep adding 3 over and over and over again?
Sure.
So our goal is to find a formula so that I don't need to keep adding 3 over and over again. So when we say a formula, it's, I'm going to make up a random one which won't work. I could say 5n minus 1. Okay, so if I plug in 1 to find my first term, we say this is a sub n, and I'm trying to find a sub 1. I plug in 1. I get 4. I think, yes, I got the first term. But what's going to happen when I go to my second term?
Not gonna work.
We get 9. So, that was a problem. We didn't get the second term. That didn't work. We'd have to try again. So I want you guys to play around and see if you can come up with the formula that
Yes.
would give us these numbers. A formula that when I plug in 1, I get 4. When I plug in 2, I get 7. When I plug in 3, I get 10. Okay, so most of you guys came up with 3n plus 1.
Oh, jeez.
Now we noticed that we added 3 every time. What is adding the same number every time really doing? Multiplication. So you guys said, well, I'm going to get 3 times n, which gets us close. We'd have 3, we'd have 6, we'd have 9, we'd have 12. So how much are we off by when we just have 3n? 1. So we call this 3 the common difference. Fancy math term for how much you added by every time. And we call this kind of sequence an arithmetic sequence. As in we're adding the same amount every time. I was just wondering if I said the word arithmetic the correct way. That's why I paused for a second. So when we're adding by the same amount every time, we call that an arithmetic sequence. Or arithmetic, I don't know which one you really say it. So we have 2 formulas for our arithmetic sequences. Explicit formulas and recursive formulas. What we found here, this was our explicit formula. This could help us find any term we want. We could plug in 1,000,000, and the 1,000,000th term would be 3,000,001. So an arithmetic sequence has a formula of the common difference, which we usually represent as a d, times our variable n. Again, n is represented as integers. We plug in 1 first, we plug in 2 second, plug in 3 third, because usually we start with the first term. Plus a sub 0. If a sub 1 is the first term, what's a sub 0?
Before the first term.
Before the first term. It's the 0 term. So if I'm adding 3 all the time and I wanted to go back to the 0 term, what would I get for the 0 term on this? 1. How do we do that? Subtract. Since we're going in the opposite direction. Yeah, this is an intro to sequences, so hopefully it is a little easier. And how can we find the common difference mathematically? If I gave you 7 and 10, how do I find the common difference between those two things?
Subtract.
Subtraction. Okay. So we also can define a formula recursively. The recursive definition has some advantages sometimes. It's not great for finding just any term. So when I say a sub n plus 1, let's say I want the second term, then I'd have to plug in 1 for n, so that would be a sub 2. But to use the recursive formula, we use the previous term plus that common difference. So I'm going to scroll back up to the formula after you've written this down. The sequence we were working with, so I can show you what I mean by that.
Is the N in the subscript?
Yes, the n is in the subscript, sorry.
It's like
Right
and.
Thought it is. So scrolling back up, if I want to know the third term, and I know the second term, so if I want to know the third term, I'm going to call that a sub n plus 1. I use the previous term, a sub n, plus that common difference. 7 plus 3 gives me 10. If I want to know the fourth term, I use the previous term, a sub 3, plus 3. So 10 plus 3 gives me 13. So recursively is using knowledge we already have of terms given to us. Whereas the explicit formula, I can find whatever term I want. Recursive, if I wanted to find the 100th term recursively, I would need the 99th term. If I'm going to find the 99th, I need the 98th. So explicit is usually, in general, more useful, but there are some advantages for recursive formulas as well. So I'm going to have you guys try this. This is a simpler subject, so I'm going to have you guys try it. Woo!
Oh, you almost got it.
Almost got it.
Sorry to interrupt your class.
Okay, so I'm going to have you guys try this, though, instead of doing an example together first, because it's fairly straightforward. Okay, so our explicit formula, most of you guys got pretty easily. Explicit formula would be a sub n equals negative 3 times n, technically plus 0, but you guys know we don't really need that. The recursive, when we're doing the recursive formula, it needs both the a sub n plus 1 and the a sub n in it to have context. If we're trying to find the fifth term, let me write it out first. Common difference. Okay, if I'm trying to find the fifth term, I want to find a sub 5. What term am I going to have to use?
A sub 4.
A sub 4 minus 3. So I would need 1, 2, 3, 4, negative 12 minus 3, which is negative 15. So I need both of these in order to have context so that we know we're finding the next term using the previous term. So then finding the 100th term. What's our 100th term? If we have an explicit formula, plug it in, negative 300. Negative 3 times 100 is negative 300. And notation-wise, that means we found the 100th term. So a sub 100 equals negative 300.
I feel like this is about to get
Oh.
going.
So we are going to talk about a different type of sequence. Before we talked about something where we added every time, or subtracted, because that's the same thing.
This was multiply.
Okay. So we already have some guesses that this is going to be multiplied, so let's check. How many boxes this time? So instead of toothpicks, we're looking at the entire box. How many boxes did I use to make this first term? 1 box. How many boxes to make the second?
2.
How many boxes to make the third? 4. So what do you think our sequence is 1, 2, 4. What would come next? 8. 16.
32, 64.
We'll put dot, dot, dot so that we're not counting forever.
No,
So we already had some guesses as multiply. What are we multiplying by every time? 2.
Those seven.
So we multiplied by 2 every time. We could also check what we add by as well. And actually something kind of fun happens when you check what you add by. If we check what we add by, what do we add by for the first one? 1. What do we add by for the second one? 2.
4.
Notice what's happening when we check our add. It's the same pattern. So if you see that happen, you should think, hey, I should probably check my multiply. I got the exact same pattern. This is actually probably a multiply, because if we can get these to match, our life is a lot easier pattern-wise. If they don't match, sometimes we can find a pattern for it, sometimes we can't. Okay, so again, I want you to come up with a formula to make this happen. Again, I would pick a random one. Let's say I have 2 times n minus 1. If I plug in 1, 2 times 1 minus 1 is 1. So that first term worked out. But if I plug in 2, 2 times 2 minus 1 is 3. Didn't work. So you need to come up with a formula, and it doesn't have to be only multiplication. We can use any math operation we want or desire to try and come up with a formula. So I'm going to give you guys a few minutes to try and come up with a formula. I must start at 1. So what we finally decided is multiplying a bunch of times gives us exponents. We said, well, we think maybe it's 2 to the n, but if I plug in 2 to the 1, you get 2. This is a problem for us. And I must start by plugging in 1. If I started at 0, I could say 2 to the n only.
Would it be 2 to the n minus n?
Okay? And minus n would just give us 0.
Oh, I meant like.
Oh,
No.
minus n to the side.
Yeah.
Okay. 1 to the side, 2 to the
No,
1.
minus n.
Sorry.
Yeah.
I was thinking of the first term.
Yeah.
So 2 to the n. Now I want to actually plug in 1. Come on.
Hey, Ms. Barton, is this your calculus class?
It is.
Guys, hey, I took AP Calc last year with her. Sorry,
did.
nice to meet you guys.
Okay.
That'd be 2
So.
to the 1 minus 1.
Man.
I was like, wait, I'm
Yes.
so confused.
Success! Okay, there's our first term. Let's try our second. We've got to make sure it works for all our terms.
Yeah.
2 to the second minus 2 is 2. Okay, it worked for the second term. We've got to check our third term, 2 to the 3. No. 2 to the 3 minus 3. What's 2 to the third? 8. It's 8 minus 3.
No! Oh no.
So we're close.
Happy.
Just kidding.
Backwards high five.
Yeah.
Okay, so we were close. We're getting closer, but we're not quite there. We know it involves 2 to the n somehow, but we want that first thing to be 1. So exponentially, how do I make something a 1 when I use an exponent? Make it a 0. Okay? So we know we're starting with a basis of 2 to the n. So, let's see. 2 to the n minus 1. 2 to the 1 minus 1 would be 2 to the 0, which is 1. Success with our first term. 2 to the second minus 1 equals 2 to the first equals 2. We're good so far. 2 to the 3 minus 1 is 2 squared, which is 4. If we did 2 to the 4 minus 1, so 2 to the third, 8. So it's worked for every term so far, which leads us to believe this is our correct formula.
Is it always 2, or is it just
Not necessarily. Why did we use a 2?
Because it's times the 2.
Times by 2. If I had 1, 3, 9,
There you go.
27, then I would have a sub n equals 3 to the n minus 1. So, I have one more though. Let's take this up one notch. How many boxes did I use to make the first picture? How many boxes did I use to make the second picture? How many boxes did I use to make the third picture? 12. So this time I have 3, 6, 12. I'm still multiplying by 2. That has not changed. Next would be 24. But if I tried to use that formula, a sub n equals 2 to the n minus 1, would I get this sequence? No. It's got to be related somehow, though, because we're still timesing by 2 every time. So I want you guys to see if you can figure out how can we change this to get our new sequence. What would we change about this to get our new sequence? So again, I'm going to give you a minute or two to think about it. Okay, so if we compare the two sequences, how would I get from 1 to 3?
Multiply by 3.
Multiply by 3. How do I get from 2 to 6?
Multiply by 3.
Oh,
About 4 to 12. Multiply by 3. So our second sequence, it's almost the same, except we multiply everything by 3. So both of them had times by 2, times by 2, times by 2, but this number out front was different. And it, in fact, is the number we started with. We started with 3, the first term. So this is the first term. And this is the common ratio. Instead of difference, we use ratio because instead of subtracting the two terms to find the difference, we're going to divide the two terms to find the ratio. 8 divided by 4 would be 2. 4 divided by 2 would be 2. So now we can come up with the explicit formula for a geometric sequence. These kinds of sequences where you're multiplying by the same amount every time is called a geometric sequence.
Oh,
Now again, there's a lot more sequences than just the two we've named today. These are the most basic sequences. I could do x squared, or sorry, n squared. If we did n squared, we'd have 1, 4, 9, 16, 25. But that one isn't one of our basic ones that we're learning about today. Just so we know there are more sequences than we talked about so far. So geometric sequences our explicit formula is a sub n equals a sub 1 times the common ratio to the n minus 1. Recursive is similar to the recursive for arithmetic sequences, except I should have put a sub n plus 1 there. Again, the a sub n plus 1 will stay there. It's always going to be a sub n plus 1. We're always going to have a sub n here, but instead of minus the common difference, we're going to times by the common ratio. If I know my fifth term is 16, and that fifth, yeah, 2 to the 5th is 16. Oh, except it's minus 1. If I know my sixth term is 16, and I want to find my 7th term, we know I take that 6th term, 16, and multiply by 2. So this time, our example isn't going to find, it's not just finding a basic geometric. We're trying to think about it in a different way. Should everyone get those down before I move on to the example? I think everyone has the explicit formula down. So I think finding a sequence itself isn't going to be super difficult. It's a little more basic. But this time they're trying to take up the way you're thinking about it, or take your thinking up a notch. The 2nd and 5th terms of a geometric sequence are 6 and negative 48 respectively. What do they mean by respectively?
In that order.
In that order. That's used in standardized tests quite often. Find an explicit expression for the nth term. So they want us to find a formula, but they didn't give us all the terms in order. We know the 2nd term and we know the 5th term. And we know it's a geometric sequence. So what are some things we know about geometric sequences? We just learned some formulas for geometric sequences. We learned what a geometric sequence was. What did we learn about geometric sequences?
They have a common difference.
Common
Ratio.
ratio. They have a common ratio. So we have to get from 6 to negative 48 by multiplying by something, let's see, 2nd to 5th term. So multiplying by something, then 2nd, 3rd, 4th, 5th. 3 times. Okay? So we have to get from 6 to negative 48 by multiplying by something 3 times. So could we kind of guess and check and solve for this? We would not divide negative 48 by 3. Divide the difference by 3. We could do that. Negative 48 minus 6 is minus 6. 54 divided by 3. 24? 54 divided by 3? No, that's 4. That's 1. 8. 18. Negative 18. No, that's not going to work out. I don't think that will actually work because multiplying 6 by 18 alone will be more than negative 48. But we could try and guess and check. 6 times 2 would be 12. Times 2 again would be 24. Times 2 again would be times 2, not add 12 again. Times 2 would be
40.
48. It's close to where we want. What's the problem though? Negative. If I times by negative 2 every time, will I get to negative 48? Okay. So we can guess and check. There's also a more explicit way to do this. I know that a sub n equals a sub 1 times r to the n minus 1. Correct? We know that's the formula for a geometric sequence. And I also know that they gave me the 2nd term and they gave me the 5th term. So I know the 2nd term, a sub 2, is a sub 1 times whatever the common ratio is, which we have found using some logic, to the 2 minus 1, or in other words,
to the first. What else do I know about a sub 2? What do I know about the second term that they told me?
It's
It's 6. So this whole thing equals 6. I also know the fifth term is a sub 1 times r to the 5 minus 1, which is r to the 4. And I know that's negative 48. So I'm kind of showing two options. Yes, we can find the common ratio here. And finding the common ratio, we figured out just using logic the common ratio was negative 2. How could I get back to a sub 1 if this is the second term? 6 is the second term. Divide. So what would the first term be? Negative 3. So that's one way. We can use some logical thinking to find it. But we can also use some algebraic thinking and do this setup. If I know a sub 1 times r equals 6, and a sub 1 times r to the 4th equals negative 48, I have two equations, and I have two variables. How do I solve something like that? Substitution. This is a system of equations. So this is a second option. What should I get by itself? R?
Wait, no.
Because R has that to the 4th, I actually think
Yeah.
probably A. So, and I'm in fact going to get this A alone to make it a little easier on me. So I'm still not working with that R to the 4th yet. So we would get a sub 1, actually no, I'm replacing that, that's the whole point of substitution. 6 over r times r to the 4th equals negative 48. What can we do with the r's? Cross out, we can get rid of 1. So we get 6r to the 3rd equals negative 48. Do we know how to solve something like that? What do we do to solve for something like that? Divide by 6. And negative 8. Then how do we get rid of 2 to the 3rd? Take the cube root. So r is negative 2. So again, we got the same answer, which is good, because if we're using two different methods, we should still be able to find the correct answer, even though we're using two different methods. We found the same answer. How do I go back and get the first term?
Just plug it into the A1 equals 6 over.
Plug it into the a sub 1. So now with all of these sequences, we can actually graph them. Our graphing calculator will allow us to get a picture of these sequences. So we still know a sub 1 equals negative 3 times negative 2 to the n minus 1. So you guys are going to need to get your calculator out. Because right now, being able to graph the sequence isn't super important, but it's going to be very important in the coming up stuff. So I wanted to practice it now.
You Alan give me one too. Thank you.
So we need a graphs
Like the
page.
kids
You
in
can either
America.
go to
Open those and
Scratchpad or
Yeah.
Thank you.
to your graphs page. I'll graph. Okay. Now obviously if I'm going to graph a sequence, I can't use the f of x. We're going to go to Menu, Graph entry edit, number 3. Sequence even has a nice sequence, and we're going to do just sequence. I have no idea how to use custom, but I can use sequence now. Okay. So if we are graphing a sequence, let's use that explicit formula we just found. We had -3 times -2, which we're going to put in parentheses, to the n instead of x. Notice it's u1 of n, u sub 1 of n. They just can't subscript it on the calculator. -1. And I thought I hit the raised 2, and obviously I did not. Come on. There we go. N minus 1. Y. There we go. Now, so far, it's only showing 2 points. Because we don't have a very big graph right now. But it's showing us our first term. Our first term was -3. Our second term is 1. It's not going to connect to the dots because the sequence is not continuous. It's a discontinuous function. So if we want to make it so we can see more of it, we can just change our window, or we could zoom out, whichever you prefer. So let's change our window, or zoom out. Or I wonder if it has a zoom sequence. Just curious. Zoom data, zoom fit. That is not, I didn't even hit that. It does not have a zoom sequence. But we know exponential functions get big pretty fast. So let's go to change our window then. Window settings. X min, we don't need really anything in the x direction that's negative because sequences start at 1. X max, let's just go to 10. Mine changed because I accidentally hit something. Tab, tab. Y min, we know these get big fast. So let's do 100, see what it gets us. -100, sorry, min. And max 100. So now we get a better picture. My use of 1. I think I can hit Control Z. I just wanted to get the label out of the way. Okay. Thank goodness for undo button. So what's going on with this particular sequence?
It became Constellation.
Okay. It's kind of bouncing back and forth because it switches from negative to positive, negative to positive, negative to positive.
Kind of like Gabriel's one.
Got it. Sorry, my brain froze for a second. Oh, so one of the big things that we need to talk about in this entire unit is, does a sequence converge or does it diverge?
It's divergent.
This one's pretty obviously divergent. Is it ever getting closer to one particular number? Let's just keep, sometimes it's positive infinity, sometimes it's negative infinity. Positive, negative. It's never even approaching infinity or negative infinity. It's just not approaching anything at all. It's just bouncing back and forth. Okay? So, we can have a sequence that does converge. Let's graph. And this one we're going to also include as an example. We're not going to do all of those graphs. I decided to stick, but we're going to do this one. So if we're going to see if it converges, we want to see what happens as we go to infinity. That's our goal with converging or diverging. What's going on with the graph as we're going to infinity? So we want to find the limit of this sequence. We want to decide, will this converge? And if it does converge, what does it converge to? So I want to take a look at the picture of this so we can get an idea of what a converging sequence looks like. Obviously, that sequence was diverging. it never approached any particular number. So I'm going to go back to the graph page. How do we get to a second graphing, or a second graph on that same graph page? Tab, right? I think that's what you said, but
Yeah,
then my
it
brain
is.
wasn't. Tab. We had 2n. Come on. It's not where I wanted the 2 to be. So I'm going to hit Control Divide first, so we get the 2 levels. We had 2n. And again, we must use n, not x, because we're working with a sequence. Minus 1 over n. Let's get an idea of what this picture will look like. Okay, so now our picture is way too big to really see this one. We're going to have to change the window again. It really does start a little bit lower and get a little bit higher, but not by much. So we're going to have to go back and change our window. Window settings, or let's just do zoom standard. That'll be so 5. Then we don't have to go enter in our settings all the way over again. So, does it look like that graph is approaching a particular number? Kind of looks like our graph is approaching 2. As we go to infinity, the y value on this graph looks like it's never getting above 2. Looks like that's what we're approaching. So we can check that by actually taking the limit. Anytime we want to check convergence or divergence, we're really thinking about what's going on as we approach infinity. Again, we're doing n approaching infinity because we're working with n's, not with x's of our function. 2n minus 1 over n. What would happen if I plug in infinity right now? Infinity over infinity. Which is undefined, but if it's infinity over infinity, what can we use? L'Hopital's rule. So we get derivative of 2n minus 1 is 2 over 1. So what's our limit as we approach infinity? 2. So is our graph from the guess correct?
Yep.
Yep, so this graph converges, and specifically it converges to 2. And we'll be seeing a lot more of these limits and stuff. Again, this is kind of the intro to what we'll be doing with all of our limits, all of our sequences. So your homework tonight, this is actually section 9.1. We went back to section 9.1, and then we'll start working on chapter 10. Page 445. 1.
We could have a test on 9.1. I'd be good with that.
But do you see why I don't understand why they put it in chapter 9?
Yeah, all these
Yeah, because
all
it's
the
like the
easy stuff
limits,
and
we're doing
just-
every other,
No. That's why it's written out individually, because for the most part it's every other odd, but then it switches every once in a while.